Hello and welcome to another Ginger Mathematician video where we're going to go through questions 8, 9 and 10 on this paper. If you're loving the content, then please do like and subscribe. It goes a long way to support the channel, and maybe you want more IB content. I do not know, but please do let me know. Right, so question 8, a game is played where two unbiased dice are rolled and the score in the game is the greater of the two numbers shown. So say I get 4 on the first dice and a 5 on the second dice, then I would take 5 as my answer. And if two numbers are the same, then the score in the game is the number shown on one of the dice. And we got the possible outcomes in our sample space diagram. Now notice there are 36 dots in total, which is important a bit later on. And our random variable here is the score in the game. So complete the table to show the probability distribution of t. And a lot of students get confused here just by the sort of unfamiliar nature of this, but let's just break this down. So when t is equal to 1, we want to work out all the results where the answer is 1. Well, there's only one result here because when the first dice is 1 and the second dice is 1, then the highest number from these is 1. And that's the only situation of that. So this is going to be then one situation out of all, okay, out of all the situations we see. And notice we have 36 dots, so it's going to be out of 36. I'm going to write this up here. So 1 out of 36. If we go to 2, let's think about how many situations there are when 2 is the biggest number. Well, we have 2 and 1, then it's going to be 2's biggest here. 2 and 2, we take the biggest number, which is 2. And then finally 2 and 1, well, this is going to be the biggest number 2. So here we have 3 out of 36 situations where 2 is the biggest number. And you can probably start seeing the pattern here as well. So if we look at 3, so let's do this in lovely purple. Well, 3, 1, the biggest number is 3. 3, 2, biggest number is 3. 3, 3, biggest number is 3. 2, 3, biggest number is 3. 1, 3, biggest number is 3. And we've got 1, 2, 3, 4, 5 purple situations here out of 36. And we can carry on in the same pattern. Again, feel free to count this at home for 4, 5 and 6, but you'll get the following answers of 7 out of 36, 9 out of 36, and 11 out of 36. And if we've covered all situations, these should all add up to 36. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25, and plus 11 is 36. So I've got all the situations represented from my diagram. Now we go on to use this to work out some probabilities. So the probability that the player scores at least 3, that's really important in the game. Remember, this means 3 or more. So if we want to work out B part I, let's go back. Which ones are 3 or more? Well, it's this, plus this, plus this, plus this. So in the exam, I would write probability at least 3 is when we actually sum, we add those fractions together. So I want to get all the marks on this, so I'm going to write my working very clearly. 7 out of 36 plus 9 out of 36 plus 11 out of 36. You could also work this out by taking away 2 and 1. And if we do this, we get then 32 out of 36. Now you could simplify this as well, but as long as we've got a correct answer at the end, this is fine. Question 2, then we want a little bit different here. So a player scores a 6, so we've got the probability of a 6 given, and this is where I put this conditional line in, given they scored at least a 3. Okay, so this is the way I would write this. And the way I would kind of teach this is, let's think about this through logically. So given they scored at least a 3, so out of the 32 possibilities, that's going to go in my denominator. Out of those, how many of those are a 6? Now, we already worked this out in the previous question. We worked out there are 11 ways of getting a score of 6. So the probability of this, and let's get the pen out here, is going to be 11 out of 32. So out of the 32 possibilities, given they scored at least a 3, how many of those it gives a score of 6. Well, that's going to be the 11. So we get our final answer here of 11 out of 32. Now, there is a formula on the formula sheet you can use to also calculate and give you the answer. Now for part C, we want to work out the expected score of the game, so the expected value of our random variable. And the way you do this is essentially work out the mean from frequency table. It's the same operation. So what we're going to do is we're going to multiply the probabilities by the number in the game. So we're going to do 136 times 1 plus 336 times 2 plus 3 times 5 over 36 and so on. So we're going to multiply the fractions by the number in the table and add those together. So if I write my working here, it's going to be 1 times 1 over 36. And you really do need to know this. This comes up more often than you think, in different contexts, of course, to actually work out the expected value of a probability distribution. So get 3 times 5 over 36. And the key thing is just to concentrate here. Make sure we're writing everything down very, very clearly. Again, this is not the only way you can write this down. 4 times 7, 5 times 9 over 36. And you don't have long in the exam to do this. Plus 6 times 11 over 36. So let's go to my calculator, pop this in, and see what we get. So we're going to type this in. So we get 1. Let's try and do this as quickly as we can. So times fraction button 1 out of 36. And it's always being very careful with brackets, etc. We have one set of brackets plus, and it was 2 times fraction 3 over 36 plus, so just being very careful. Again, you can skip this part of the video if you do not find this particularly an interesting process that I'm doing here. So 5, and you can see what buttons I'm pressing on the calculator. So then we get 4 times 7, down we go, 36. I'm sure in my analytics, like this part of the video is going to be skipped. I accept that. That's not a problem. Yeah, do like and subscribe as I'm doing this. 9. This is where I really don't want to make a mistake on camera. I'll do my best not to. Plus, open brackets. We're almost there. 6 times, close brackets, 11 over 36. This is where I really do pray I do not make a mistake. And we get our answer of 161 over 36. So we pop that in. Again, you can leave this as an improper fraction. That's absolutely fine. Or you can make this into a decimal or a mixed number. That is up to you. Okay, so there we are. Got the answer. No, didn't make a mistake. That's really, really nice to see. And you can see where you pick up all the marks for all 7 marks. This is a question that if you're aiming for those middle grades, or grade 4 or grade 5, you need to be getting these right. And you can see the maths here isn't particularly tricky. So this is a good opportunity to snap up those marks. Right, question 9. This is a tricky question in the middle of the exam. So we've got some complex numbers here. So remember, I here means the square root of -1. So this is a sign, this is complex number work. So consider w is equal to iz plus 1, where w and z are complex numbers. This is what the c means here. And find w when z is equal to 2i. So what we're going to do is we're going to copy out this expression here and replace the z with a 2i. And if we do this, well, 2i times I, that's equal to 2i squared. And remember that if I is equal to the square root of -1, it's a key fact to know here, I squared is equal to -1. So we replace the I squared with -1. And if we do this reasonably simple calculation, we get to -1. And now it wants us a different substitution here. So this time we want z equal to 1 plus I. So again, we do a similar process. We replace the z with 1 plus I plus 1. Lots of i's and 1's, so make sure you know the difference between them. You can see them. So if you multiply out the single bracket here, we get 1 times I is I times I is I squared, and 1 stays as it is. Remember, I squared is equal to minus 1, so we get I minus 1 plus 1. The numbers cancel, and we're left with just I for our 3 marks. On to question B. So point Z on the Argand diagram. Now remember what an Argand diagram looks like here. So let me just draw this in. Remember, this axis here is the real axis. We're going to use this diagram in a moment, and this is the imaginary axis. So as soon as you see Argand diagram, you need to be familiar with this kind of diagram. And point Z can be transformed to point W by 2 transformations. So notice W is equal to IZ plus 1. And it wants us to describe the 2 transformations. So what effect does it have when you multiply z by I, and then what effect does it have when you add 1? And remember, working with an Argand diagram here, which is important. So let's consider what happens when you multiply by I. So let's make z a normal number. Let's just say make it 2. So if we multiply that by I, then we get 2I. So on an Argand diagram, what happens here is if we start with 2, which is on our real axis, if we multiply by I, we get 2I. Well, 2I is simply up here, where this distance is the same. So it goes from here to here. Say we have the number 2I, and we multiply that by I, just so you can start seeing the pattern. Well, 2I times I is equal to 2I squared, which is equal to minus 2. And minus 2 on our diagram is down here on the real axis. So then 2I would come to here. And you can continue this process, keep multiplying by I, and what hopefully you see here is each time the number gets rotated, or z gets rotated around. Now let's think what kind of rotation this is when we multiply by I. You may have learnt these facts off by heart. Well, it's a rotation. The center point is in the middle because these distances never change, and we're going 90 degrees each time. So the first transformation here is a rotation of 90 degrees, and we're going anti-clockwise in this case, and the center is equal to 0, 0. One thing I recommend is really being familiar with these Argand diagrams, understanding what's happening when you're adding, when you're multiplying various forms of I and numbers. And now we need to think, okay, what does the plus 1 do? Now, remember, this is not a Cartesian graph here, this is an Argand diagram. Remember, this is our real axis. If we add 1, what happens is we just go along this axis here, 1 unit. Now, how do we write that in terms of notation? Well, this is a translation. We're just moving, we're just shifting number. And in this case, we're moving along the real axis. That's our so-called x-axis, if you're used to Cartesian coordinates. And so that's going to be a translation of 1, 0. So 1 along the real axis and 0 along the imaginary axis. So this is a really interesting question. I haven't seen a question like this so far on this course. And combining your understanding of transformations also with your idea of complex numbers. Right, and let's go through the very last part here. So hence or otherwise, find the value of z when w is equal to this. Now I always take an algebraic approach when I have the opportunity. So what we're going to do here is w is equal to 2 minus I. So I'm going to replace the w here with 2 minus I. This is the algebraic approach to take here. And we want to work out z, so we want to make z the subject. The way we can do this, we can do some rearranging here. So I'm going to add I on both sides. So we get 2 equals iz plus 1 plus I. I'm then going to minus 1 from both sides. So I get 1 is equal to iz plus I. Now this is a nice trick to know with also doing with functions as well, with inverses, is I'm going to take a factor of I out here. So I'm going to take out I. What do you multiply I by to get iz? Well, just z. What do you multiply I by to get I? Plus 1. Then I'm going to divide both sides by I here. So I get 1 over I is equal to z plus 1. And then finally, I'm going to minus 1 from both sides. And if I do that, I get z is equal to 1 over I minus 1. Now, it's not very clear exactly how they want the answer left here. A trick you can certainly do here is we can actually simplify this in the following way. So I'm going to change this minus 1 to minus I over I. Because remember, if I cancelled this, this would just equal 1. This means we can then combine the fractions to get 1 minus I over I. And we can obviously leave the answer like this. If I check the mark scheme, okay, they're happy with this, but they want to simplify it down further. That's absolutely fine as well. So if we want to simplify this, we can then just multiply top and bottom by I. If we do that, we get, well, I brackets 1 minus I on the top. We get I squared on the bottom. I times I is I squared, which is minus 1. It's not entirely clear in the question if they want to simplify it this way. And then we can just expand the bracket on the top. Let me pop this up here. So we get I times 1 is I minus I squared over minus 1. We're almost there. And then let's just simplify this first of all. So we get I plus 1 over minus 1. And then finally divide through by minus 1, getting minus I minus 1, which is what the mark scheme wanted. So it's not entirely clear they want it written in that way. I was tempted to just wait at this part and leave it like this. But if you wanted to rationalize the complex number there, then this is the way you'd go about doing it as well. A fair bit of algebra involved in this kind of process. You can check through the answers that are provided by the IB, and you can see they did it slightly differently here as well, which is an interesting approach. I took the more algebraic approach, which is approach 2. Okay, and question 10, a lovely graph theory question. So an engineer plans to visit 6 oil rigs in the Gulf of Mexico, starting and finishing at A, so that's going to be the vertex deleted, I assume, and the travelling time in minutes between each of the rigs is shown in the table, and we can represent this by a graph. This is true. And we're going to use prims because we've got an adjacency matrix here. Find the weight of the minimum spanning tree. This is a phrase you should be really familiar with on this course. Of the subgraph of G obtained by deleting A. Yep, so we're going to delete a vertex and we're going to start at B. And then list the order in which the edges are selected. So let's do this process. We're going to ignore A for the moment. We'll come back to A shortly. So I'm going to cross out A. And we're just going to focus on the other nodes here, B, C, D, E, and F. So we're going to start with B, because that's what we're told to start with, starting at B, and we're going to work out the different edges we need for this minimum spanning tree. So the first thing we do is we go down our column of B and look for the lowest number. That is going to be this one here. So this is going to be BC. That's going to be our very first edge. So this is going to be 46. Okay, and at this point then we are going to go over, we need to cross out B as well because we've already chosen B, and we're going to go over to C. And now from the two lists, this is really important here, from the two lists we then need to choose which is the lowest number. So not just the C column but also the B as well. Notice the lowest number here is this one here, D, so that's going to be 58. So we're going to go BD is 58. And now we circle D, and from there we are actually going to look for the lowest number that they share. So I should have crossed out C from before. And if we look down all the lists here, you'll notice this is the smallest, so this is DE. So we'll pop that in, which is 23. And now we're looking for the last one here. So now we want to look for, we've got DE now, the lowest out of all the lists that we have here. And you'll see the lowest one that we have here is EF. Oh, sorry. There we are. So is EF with 47. So that's going to be our very last edge here, which is 47. Notice we've got 5 nodes, so I know with using Prim's algorithm, there's going to be 4 edges. At this point, we want to work out the minimum spanning tree and the weight of it, so we need to add up all those edges together. So we can do this in our head. So 47 plus 23 is equal to 70, plus 58, 128, 134, 174. So this is going to be the weight of the minimum spanning tree. And we pop that in like so. And that is going to be our lower bound. Okay, so that answers question 2 as well. So that's going to be our lower bound here. Right, and then we go on to question 2. So now we need to find the lower bound from the minimum spanning tree of those 5 nodes for the travelling time needed to visit all the oil rigs. Now we deleted vertex A in the previous question, so what we need to do is add in 2 edges that go into the graph from A and then come out from A. So if we look at A specifically now, so we're looking at this part here, we want to find the 2 smallest edges here, which are going to be AB at 55 and AC at 63. So in order to complete the travelling times needed to visit all the oil rigs, we need to put in AB is 55, AC is 63, and we need to add those to the minimum spanning tree of the previous questions. So to work out the lower bound, we're going to add in 55 plus the 63, the 2 lowest from A, going in, going out, and also add on the 174. And if we add those together, we get 174, 237, 42, 292, which is 292 minutes. I think I've added that correctly. So that answers A part 2. And then part B, this is just an understanding of how this actual process works. We want to work out how an improved lower bound might be found. Well, we can simply delete a different vertex. So we assumed at the start that we want to delete vertex A, but notice we could have deleted any of the vertices and started at B instead. So we could have deleted C and then started at B. That would have also worked as well, and that will give us perhaps a better lower bound. Again, it's perhaps, it may not, it may do, but that would be the process to go by. You need to delete the different vertex. Okay, hope you enjoyed that video of question 8, 9 and 10. Again, please do like and subscribe, and there'll be more videos coming out shortly. Okay, bye for now.